What breaks when you crack a glow stick? How does this magical wallet work? And can I build a glow-in-the-dark remote to fix the one my dog chewed up? These are some of the 9 video topics in this compilation of shorts, but don't worry, I filmed everything horizontally in anticipation of this video. Enjoy. If you've ever cracked a glow stick, you know that it makes the glow stick glow. But let's check out what's going on inside. Opening it up and you of course see the glowing fluid coming out, but you might not be expecting to see a bunch of shards of glass. That's because when you crack a glow stick, you're actually shattering a glass vial that's originally separating the two solutions. Here I'm cutting open a glow stick that hasn't been cracked yet, and now you can easily see this glass vial. By the way, you absolutely shouldn't open these glow sticks in general, and definitely don't break the glass vial outside the tube unless you want to mess. I wanted to combine these two solutions directly outside the tube, so I first drained the outer liquid into a small beaker. Then I dried off the tube to remove residue and smashed that glass vial inside a glass container, and as you can see, it won't glow yet. Then I used a syringe to suck it up and added it directly to the beaker, which created a cool glowing drop effect that didn't immediately mix very well. There's something about combining these solutions in different ways that is so beautiful. Anyway, these skinny glow sticks require you to crack them multiple times to make the glow stick glow throughout, but it's still a glass vial inside. It's just so skinny that even after cracking it, the liquid doesn't come out very easily and you need to break it multiple times to speed up the mixing. Here's a few cool items that seem like magic. First up, as you can see here, this wallet is completely empty. However, by folding a dollar bill and placing it inside the wallet, it almost appears like there's two dollar bills. One tucked here by the bands in a cross pattern and another tucked in by the horizontal bands on the other side. This is of course the same dollar bill, but adding more dollar bills to this wallet only makes it more confusing, not less. This works because the wallet seems like a single piece that hinges, but it's actually two completely separate pieces held together by two sets of elastic bands that are in tension with one another. That means folding the wallet actually only changes which set of the elastic bands are pinning the dollar bill to the wall. The dollar bill itself doesn't move. I'm not sure understanding that makes it any less mind-blowing though, especially when adding multiple dollar bills to different sides. Next up is this pressure puller, which is a relatively flat piece of rubber when in the neutral position, but when you close the handle, the center of the rubber gets pulled in. That means when you place it on a flat surface and close the handle, a vacuum is created, which allows the tremendous force of atmospheric air pressure to keep the two items together. What's amazing about this is it shows just how strong air pressure can be. Using it on this pretty heavy coffee table, and I can lift up the entire thing using air pressure alone. I've shown flash paper in a few very cool experiments, but I've never really talked about how awesome it is on its own, especially watching a flat piece of it burn in slow motion. Regular paper burns much more slowly and leaves behind some ash and residue, but flash paper leaves almost nothing behind. That's because paper is primarily made of cellulose fibers, which is the same as flash paper, but the flash paper has been chemically altered by soaking it in acid. Hence why flash paper is also known as nitrocellulose. This chemical alteration makes the flash paper have its own built-in supply of oxygen within the material itself. When ignited, this causes nearly complete combustion that happens extremely fast, meaning almost all the products of this reaction are gases that you can't see. I'm not sure burning this will ever not be fun, especially when messing around with a magic wand that ignites the flash paper within the barrel. However, perhaps my favorite shot is when I placed a piece mostly flat on a brick and I was able to capture a pretty epic shot of the flash paper burning in super slow motion, which only leaves the tiniest of traces that it was ever there at all. I'm going to use this massive vase to recreate a large-scale version of this beautiful science demo. First, I need to fill up a container with a bunch of water. Then I'm going to pour some vegetable oil in, which already looks pretty cool on its own, but importantly, because it's less dense than water, it rises to the top. And since it's non-polar, it doesn't mix with the water, and thus once it settles, it creates a distinct layer on top. This food dye is water-based, so when dropped in water, it will disperse, as you can see here. However, adding these drops to oil and they stay almost perfectly spherical. Even after stirring it up, they won't mix, but this does make individual drops that are much smaller. Now I simply pour this into the large container, doing my best to spread out the drops, and all I have to do is wait. As expected, the tiny food dye drops will sink through the oil slowly. That is, of course, until they reach the surface of the water. At that point, the dye disperses in the water, which over time creates a beautiful display. I thought the smaller drops would look the best, but I tested out some large drops too, and I really like how you can see them falling through the oil before bursting into the water. I'm speeding it up here quite a bit, but I think these are even more beautiful than the tiny ones. This is a 2-liter soda bottle before it's been expanded, and I'm going to use it to make a simple DIY lava lamp. First, I'll fill up this preform with vegetable oil a little bit more than halfway. Then I'll add one of these tub tint tablets, which as the name implies will change the color of your bath because they contain a dye as well as baking soda, citric acid, and sodium carbonate, meaning it dissolves in water. Notice how when I add this tablet to the vegetable oil, it sinks but doesn't start reacting. Next, I'll add a bit of water, which is more dense than the oil, so it will sink slowly to the bottom. Once it finally comes into contact with the tablet will start to fizz and change the color of the water. At first, nothing seems to really be happening here. However, as more and more gas accumulates, larger bubbles will break through the surface and rise to the top. If you look closely, these rising gas bubbles will bring red water drops with them. However, once these drops get to the top, the gas will escape out the surface, causing the water drops to once again be heavier and sink. Over time, it starts to become more and more beautiful, and this cycle of rising and falling water drops will continue until the tablets completely dissolve. At that point, all the water drops will eventually sink back to the bottom. Ever wish your TV remote glowed in the dark? Well, I sure didn't, but when my dog recently chewed up my TV remote, I noticed that the circuit board was almost completely intact still. This circuit board is the brains of the TV remote. All this casing nonsense is just so it feels nice and is durable. So as you can see here, simply placing the batteries directly to the circuit board and then completing the circuit with the additional spring, and the remote still works. To make a new remote case, I took rough measurements of all the buttons and created a simple 3D CAD model for the top plate. I had guests coming over to watch Survivor the night I did this, so I tried to do it quickly, but that actually didn't end up saving time because I forgot a few things, such as how a 3D print will shrink slightly compared to the 3D model due to thermal contraction, meaning the smaller buttons didn't quite fit. I also didn't pay close enough attention to how some of the soldered ends and components on the circuit board were sticking up, preventing the top panel from laying flat with the buttons. I was a bit more careful designing the bottom carriage, and although this was definitely a bulky and suboptimal design, I was happy with the nice and satisfying press fit for the top panel, which was actually pretty secure on its own. The batteries will need to be replaced, so I need to make the back piece removable. I could have made a more complex version of a compliant mechanism like most remotes use, where the plastic deformation really locks it into place, but I just went with the simpler one. Another press fit, and I figured I can secure it more later if I need to. Why spend $10 on a new remote when you can spend like 8 hours recreating a slightly worse one? But hey, at least it's glow in the dark, which is pretty cool. Ladies and gentlemen, the time has come for a chocolate ball Melttop, and boy was this a surprising finish. Chocolate lint balls have been placed on the ends of each metal rod, as you can see here, and a blowtorch will be heating the centerpiece. The goal is to hang on to your chocolate ball for as long as possible. On the left end, we've got the heavily favored stainless steel, right next to the historically bad copper. Next is brass, who's expected to make the podium today, followed by another underdog, aluminum. And lastly, iron, who should take home silver. These power rankings are based on each metal's thermal conductivity, aka each metal's ability to conduct heat. 25 seconds in, and copper's already showing signs of weakness, and just like that, as expected, copper's out of the running. Aluminum is expected to fall next, and you're definitely seeing signs of slippage, but wait a minute, brass has some movement too, and wow, a photo finish. Instant replay shows brass completely choked and aluminum takes home bronze. Iron looks strong early on, but after another 50 seconds or so, it looks like they could be in trouble. And just like that, stainless takes gold and remarkably held on longer than the aluminum rod itself. Absolutely unreal it broke off before even the stainless steel's chocolate drop, which came long after the fuel was removed, around 4 minutes and 20 seconds. Since cucumbers are easy to cut through with a knife, I decided to make a reverse guillotine where I can drop a pretty respectably sized cucumber onto the knife to slice through it, at least partially. I originally wanted to make this an engineered bet where I'd attempt to calculate how much of the cucumber would be sliced. I was going to use the width of the knife near the edge and a shear stress value at failure for Nigerian cucumbers that I found in this paper. That would allow me to estimate the shear force exerted on the cucumber by the knife to slow it down, but when I did that, it was actually smaller than even the force due to gravity from the weight of the cucumber that I was measuring, which means it would theoretically never stop slicing through. Obviously, that calculation is missing additional forces like that of friction on the walls of the knife, and since that wouldn't be trivial to incorporate, I decided to bail on the calculation, but I already 3D printed the knife holder, so I figured why not see what happens anyway. The drop wasn't perfectly straight, of course, but at this height it easily sliced all the way through. Trying from a lower height and it still went cleanly through, although the cucumber was a bit curvy. I guess this knife is just too sharp for the weak cucumber, and it seems only a small drop like this will stop the cucumber from falling all the way through. Before you head out, I wanted to let you know I'm releasing a multiplayer video game this summer called Stick Scholars, which is an online social deduction party game where players must parkour to school, answer trivia, and hunt down a hidden class clown who's sabotaging to try and make the entire group fail. You can watch the trailer for all the details, and if you're interested in playing, I'd love for you to wishlist the game on Steam. Thanks for your support, and I hope you enjoyed this video.